반갑습니다. 조윤호라고 합니다. 사실 국내에서 하는 발표 회의여서 이 국문으로 제작을 해야 될지 영문으로 제작을 고민을 했는데 일단 영문으로 제작을 했기 때문에 양해가 안 되면 제가 영어로 발표를 진행하도록 하겠습니다. 그러면. So since everyone is very international for this exhibition, I'll continue my presentation in English. So there's been a big drive in sustainability in our industry, and I think because of that, recyclability has been the key word for our industry. And in that manner, it seems thermoplastic has been the driving factor in most of our customers lately. But as a thermoset prepreg manufacturer, we want to discuss: is thermoset over, everyone? Is there any room in the future for thermoset plastics? And we're trying to say there are, and I'd like to explain why. But before that, 그 다음 슬라이드를 어떻게 컨트롤하면 될까? To explain a little bit about our company, Hankuk Carbon has been producing composites, especially glass fiber prepregs and carbon fiber prepreg, since 1984. We have been traditionally very strong in manufacturing unidirectional and fabric prepregs for fishing rods and golf shafts and mainly sports and leisure sector. But over the years, we have been the powerhouse in South Korea in our own national defense program and for some sort of government-led programs. And due to that, we now have a very good understanding of aerospace or maritime industry or defense industry. And we are developing our staff and our factory not only to support sports and leisure sector, but for sectors where traceability and standard deviation of quality is important. Just to give you a brief idea, we have over 50 million meters squared of yearly capacity, and we have 9 plants, 7 in Korea, 1 in Vietnam, and 1 in Slovakia. So we're well positioned to support global operation. Just as I mentioned, we are trying and we are currently supplying products to automotive, especially for EV battery covers, which require fast curing and high flame resistivity and good durability. In aerospace, we recently have qualified our glass phenolic and carbon phenolic and aramid phenolic prepreg system to Boeing, and we will soon to be listed on their QPL. For sports and leisure, through our customers in south of the earth, in South America, in South Africa, and in Australia, we have a big market share in spars and the yacht industry, and we're continuing that sports and leisure maritime sector. In construction and energy, Korea is very famous for ondol culture. If you have been to Korean traditional homes or even latest built apartments, you'll know that South Korea is one of the few countries in the world to have underfloor heating systems. We have very cold winter. So traditionally, our flooring material cannot cope with that heat variation. And it's one of the key sector where we've been very strong. And by having that unique culture in Korea, we were able to develop a glass fiber paper which could be used as a reinforcing material for natural wood or plastic-based underflooring materials. Another sector that South Korea is very strong is in shipping industry, especially for LNG carriers, especially with the current Russia-Ukraine war. Now, the majority of LNG, natural gas, is transported over water, And our company is applying approximately 50 to 60% of the global market share in that sector. It requires a high insulation property in cryogenic temperatures and high mechanical properties. So even though we're a small company in Korea, we have very unique strengths, which I've told you in construction energy is kind of flooring. In maritime is for cryogenic insulation and for gas barrier systems. And for automotive, fast curing, some sort of fabric or UD stacking, and with minimal preforming, making products very rapidly. So these are the kind of key USPs of our company. So what does that lead to? Where is the future for our country, and where's the future for us? Traditional industries in aerospace, it seems Hexcel is here, and they're very strong. Solvay is very strong. Toray is very strong. We understand that as a latecomer to the industry, we're limited. But what about the future? The future where urban air mobility is throwing numbers that, as an industry, we've never experienced before. This will kind of, we believe, will give us some opportunity, because existing companies cannot handle all the capacity. But also because, as I mentioned, from automotive industry, where fast curing is required, where weathering temperature exposure is much more severe than existing situation, where battery technology will be very strong, where semiconductor industry will be very strong. And South Korea seems to happen to have all of that. We're very strong in automotive, we're very strong in semiconductors, and we're very strong in system integration. We're good at building things. And urban air mobility seems to integrate all of those technologies. And we are preparing our company for that future in these 4 main points. Structural parts, which we believe will be the most parts that will be similar to existing industry. But for other propellers or interior parts or secondary class structures will require a much more cost-effective and a much more rapid manufacturing process. And furthermore, where in the era of urban air mobility, each mobility will need to be able to communicate to each other. We're talking about 5th gen, 6th gen telecom situation. A lot of people neglect how much electromagnetic noise that the world we live in. Even though we cannot see things right now, our mobile phones, our laptops, our telecom communications, there are so many noise existing from power lines and motors and things that, in fact, the biggest resistance from communicating from one vehicle to the other is this noise. So how do we overcome this? I think there's a solution in our materials, which is EMI shielding. I think our hardware and our prepregs and manufacturing, EMI shielding will be a key standard in future. And we're deriving such technologies from, interestingly enough, from stealth technology that we're working on, radar absorbing materials, additives, the components that we can put in our prepreg. And this is the kind of technology I think intermediate companies, intermediate composite materials companies should be going for. Just to show you some pipeline of our structural parts. Currently, it's under validation. What do I mean by under validation? It means we're undergoing SMA tests. We're building our own data card, and we're building the DB for that. But for industrial and yacht industry, it's already been proven and tested, and we are providing the data card for that, for high fatigue durability and etc. For interior parts, as I mentioned, glass fiber phenolic has been. We are ready. We are producing that, and the main points are: it needs to be able to self-extinguish, high fire resistance, resistivity, low smoke density, low toxicity. And what I've prepared is under validation by Boeing, but we have been validated. Hopefully, we'll have some good news in the future. Regarding our fast cure, we are hoping to, not hoping to, but our chemically, our cycle time is under 4 minutes at 150 degrees Celsius. We have faster curing system, but what we have realized is no matter how fast we prepare our chemical systems, if our customers are not ready to prepare the materials in that time, it no longer makes sense for us to prepare a system that their manufacturing process does not work. And what we realize is that even the best of the teams, who are the most mature and who have the most experience, seems to have they need at least 3 to 4 minutes to prepare for the next curing cycle. Regarding our flame retardant resin formulation, there are many different kinds of ways of going around that, whether it be unsaturated polyester kind of SMC, or whether it be our FC9XL, which stands for fast cure situation. If you have time, please come and visit our booth to give you in-depth discussion. But what I'm trying to say here is that thermoset prepregs are cost-effective and very good in flame-resistive properties and should not be overlooked at. I kind of want to fast forward this and discuss about the LCA, so please understand. But within our portfolio, we have a honeycomb core, foam core, and nonwoven core business as well. But this is the point I wanted to mention. And LCA is considered a life cycle assessment. It is not what is commonly overlooked is how much carbon dioxide do we produce to manufacture a material or part. The whole concept of the LCA is during the life cycle of its part, how much energy are we putting in? And it starts with raw material extraction. For, let's say, steel, iron ore, steel ore, carbonization, heat preparation, et cetera, cold pressing, all of that. For us, it would be glass fiber would be from sand, melting, to a fiber, to fabric, to a prepreg, or RTM, or other kind of part. And then end of life, we'll disintegrate it, make it into chops, or through different lots of recycling technology, we'll get there. But the point is, technology is there. Days and eras of putting into the landfill are gone, and we'll see why. For prepreg compression molding, it seems to be our solution to thermoset in LCA perspective. A lot of sheet mold compounding or thermoforming, it seems to be used. So our customers who are already used to, cold pressing, using presses seems to be the most cost-effective manufacturing process. And from a prepreg's point of view, this is the closest solution. And our current technology is giving approximately the mold temperature to be 120 degrees to 160 degrees, and cycle time to be 4 minutes. And the point is it's hot in and hot out solution. So we don't want any thermal change in our pressing. So once the material is ready, it goes into the press, and then once the materials is done, we want to take it out, and we want this to be a rapid process. How much energy does it take to produce a material? These are some figures for you to just take into account. Approximately to make 1 kilogram of steel, it takes up 35 megajoules. And for aluminium, it takes about 219 megajoules. And for glass fiber, it's only 30 megajoules. And for carbon fiber, as you must understand, takes approximately 300 megajoules. But what's interesting is the recycled part. Recycled steel is only 10 megajoules, and recycled aluminum is only 15 megajoules. So from LCA perspective, when in future, the vast majority of materials are going to be recycled, our target energy cost to produce our materials should be at recycled and recycled steel area. So to give an in-depth study on LCA, we try to calculate a particular part. And this is an actual existing program which I cannot share, but if it was made in steel, if it was made in aluminum, if it was made of glass fiber thermoplastic component and a thermoset program, how much energy would it take to manufacture this part? Based on that, it follows the mechanical properties. For steel, it approximately takes 7.8 kilograms and takes 764 megajoules. For aluminum, for that mechanical properties, we believe 2 millimeter thickness does the job and takes 3,300 megajoules. But the current UL2596, which seems to be the basic standard for EVs, is that it needs to require a high thermal resistivity, flame. It requires high flame retardancy, and it requires over 1,000 degrees Celsius for a certain period of time. I believe it's 30 minutes. So can aluminum withstand that? I don't think so, but for your reference, just to give you an idea, glass fiber components is very, from energy perspective, quite effective. Energy consumption in the production side, if you compare thermoset and thermoplastic, there are two main differences. I think it's in pressure and in temperature. There's no thermoplastic solution which can be compared in terms of manufacturing process. Forming pressure requires at least 100 bar per meter squared. And for thermoset, it requires less than 30 bar. For forming temperature, most thermoplastic requires over 200 Celsius to prepare the materials. And for thermoset, our minimum temperature starts at 90 degrees Celsius. So from energy perspective, putting the material to that level of forming temperature is, in this perspective of LCA, is excess energy. And from pressure side as well, more pressure means more energy. And the other part of thermoplastic is it requires a cool down, whereas thermoset, you only need to heat it, and you need to activate it, and you need to keep it there, and then the reaction does its job. So next, before we move on, if you look at the bottom right chart, it shows how much energy approximately it costs to use in energy and sheet mold compounding, which is a bit similar to PCM, pre-preg compression molding, is quite cost-effective compared to injection molding, which is approximately the same amount of energy required for thermoplastic sort of sheet mold compounding. So what about design flexibility? Right now, in all thermoplastic press forming, it requires laying up on the plate and then heating it to 200 degrees Celsius and then placing into the mold and then press and cooling. there's very little room for preforming, or there's very little room for adjustment in that stage. It will require a very sophisticated robots or sophisticated equipment to handle such material at such temperature. But I think this is the beauty of prepreg, because you don't need to go to that temperature. You can move prepreg in room temperature, and you can preform, and you can put it material. You need to warm it up maybe just into room temperature is enough. And from that perspective, if you want to design or manufacture a very deep profile where it requires lots of reinforcement in the corners or reinforcement in particular areas, that's something very difficult to do with thermoplastics. So what we're trying to say is thermoset, you don't need to use as much of the resin. You can put more fibers to do the job, and therefore higher mechanical properties can be achieved. And what does that mean? It means we can make the same material but lighter. So as shown for the EV battery cover, thermoset parts can fundamentally be a lighter part than thermoplastics. And from the life cycle assessment point for our end user, saving that 1 kilogram can make a big difference in the whole LCA of our end user customer. But everyone say, thermoset recycling is not there. How are you going to recycle thermoset? And I think it's because the technology is not fully viewable, it's not viable, or people don't think it's viable. But I think everyone in this room understands that there are already so many solutions that's given in the market. And even though it is not being in a mass production level, already core technologies in mechanical recycling, thermal recycling, or chemical recycling. I'm a big fan of, personally, a thermal recycling fan. But we have other speakers here who can explain for this better. But South Korea has very cost-effective electric, 50% approximately is nuclear energy, and another 25% is from solar and wind. So only right now, coal and LNG is accounting 30 to 40%. And for ourselves, we already have 60% of our energy output is covered by our own solar panels on our roofs. So 40% of our energy we use from the Korean electric company. And already 50% of that is nuclear or clean electricity. So our company is already nearly 80% to 90% ready for net zero electricity. With that basis, if we can bring in such technology in-house, I think personally we can be one of the very first companies who can achieve to sell prepregs and components and retrieve the components and recycle it on our site and redeliver those parts. I wanted to explain a little bit more about thermal recycling. Just to give you an idea, compared to thermoplastic recycling, where you need to physically crush it and then heat it and then make it into pellet type, which seems to be the most viable recycling technology for thermoplastics. For thermosets, however, we can use the epoxy or the hydrocarbons or the chemicals and we can use that energy to burn it off again, and then help the process of the pyrolysis. And the energy required for reusing those components is only 7.04 megajoules per kilogram. If we don't use the energy, and let's say we use the, it's a recyclable epoxy, and you want to retrieve that epoxy and then use it somewhere else, it's only approximately, at maximum, 50 megajoules. And the reason why I'm trying to put this figure in is, if you go back to our slide, this one, where we're comparing thermoplastic and thermoset. To manufacture a thermoplastic composite, it requires, per kilogram per component, requires over 200 megajoules. So from an LCA perspective, if we can say that, okay, yes, thermoplastic can be cost-effective in recycling part, what about the manufacturing part? If thermoset can be more effective in the manufacturing and in terms of the whole LCA perspective that we're competitive, then we think thermoset can also be a very viable and eco-friendly solution. Again, chemical recycling. How much energy does chemical recycling? This is a Korean company who does this, but they say they can do this in through pyrolysis. It requires about 48 megajoules, as I mentioned, under 50 megajoules. But for chemical, it requires only 35 megajoules. Although I did not take into account of how much energy are required to synthesize such chemicals. So there is an argument there. But for reusable epoxy point of view, I think Swancor is going to do a better job of explaining this. But it seems our industry, in our thermoset industry, everyone is preparing our own solution for recyclability issue. So in conclusion, steel requires, for the same components, 7.8 kilograms. Glass fiber reinforced thermoset only requires 3.6. For part production energy perspective, compared to thermoset can be done on low pressure, low temperature, and we have higher design flexibility and a higher permeability, meaning we have better FAW, fiber air weight. So we can optimize more effectively. From recycling energy, so CFRP, to manufacture it, will cost 290 megajoules. But as I mentioned, through chemical refining or recycling, or through pyrolysis or other kind of more effective recycling, but we can achieve at 40 megajoules, which is now very similar to aluminium and steel. And we're not far off. So to end my presentation, we are building our new R&D center in Seoul, in Magok area. And our presentation today is hinting at the effectiveness of thermoset, but requires more support from our industry to be more accurate. Exactly how much more? Let's say if we save 1 kilogram in a 20-year life cycle of a vehicle, how much energy are we saving there? How much money can we put into that? I think this needs to be a collective effort, because what we're trying to do at the end of the day is trying to put our material in an end user who is not familiar with composites. So we have to educate them, and we have to educate them, and we have to show with numbers and facts why composites should be used instead of aluminium or steel. So hopefully, with our new R&D facility, which we only use approximately 60% 40% of the room, we are hoping we can collaborate together. We would like our international partners to come to Korea and utilize our facility. We will have a state-of-the-art pressing capability, chemical labs, and we will have our R&D team to collaborate, communicate, debate, and collectively think about the future of our industry. Thank you.
예, 감사합니다. 한국 카본의 비전, 더모셋의 그 잊혀지기 쉬운 그 서스테이너빌리티, LC의 관점에서 아주 잘 설명을 감사드리고요. Now is time for Q&A.
Thank you, Yono. You are third generation. I always thanks for your company collaborating for our association as a partnership also. Your mother company started more than 50 years ago, and today you explain about the Somerset, the prepared systems. But I will say, I'm hearing this time, someone say Somerplastic, someone say Somerset. But I will say, even we are manufacturing of Somerset, it's like, who do you like, mother or father?
Yeah.
Which one is more delicious, apple or banana? Yeah. So actually the composites, carbon composite or glass composite, depends on the requirements, performance requirements. We can use some part of that is with the Somerset, some part of that with Somerplastic. And I will say in the futures, we can say like a combination or hybrid system. So you can develop hybrid system like a Somerset plastic. So because you are not only the Somerset player, so you need to develop or making some kind of collaboration between the Somerset and Somerplastic. Second things, you can see here that we invite European players and American the important supply in the market. So as your responsibility for third generation, I will say, recommend you, here we have a very important supplier in the market, Hexel or German company CU and Sikomin. So to grow your company globalization, you do better to collaborate with them, not competitions. So for the global supply chain, you do better to contact them, like all the player here, some kind of collaboration together. Thank you.
Thank you. I hope you don't misunderstand me. I'm not trying to say thermoset is the best. I'm definitely not saying that. So that's what I'm trying to say is that thermoplastic is also not 100% the right answer. But what I'm seeing and what I'm hearing seems to be that only thermoplastic seems to be the interest of a lot of our major customers. And I'm just trying to take this opportunity to address the benefits of thermoset plastics. But personally, I am a strong believer in the hybrid solution. I'm a strong believer in the benefits of thermoplastics. And the future, as Chairman Park has said, is we, as a company, need to be able to handle both solutions. So I'm always open to hear and discuss any ideas in the industry. Thank you.
예, 하나 받을 더 시간은 있을 것 같은데 혹시 any questions, comment? 예, 뭐 너무 열정적으로 발표를 해주셔가지고 시간이 조금 지체됐습니다. 감사합니다. 예.